All right. So, we know what a tree is now. It is a data structure that's made up of a bunch of nodes, and well, we were talking about binary trees. A bunch of nodes, and you can have a left child or a right child. You don't have to have either. You can make it null, just like linked lists don't have to have a next. That's the end, right? It's the bottom when it's a tree. You can also deal with parent pointers, people above you. Where did I draw that? Here. And so this is our struct definition of a node in a tree. This will depend on the kind of data you have. So maybe this could have been a templated kind of struct. That would totally work. But as far as pointers go, you have a left, a right pointer, and then potentially a parent pointer if you want to use that. All right. Usually it's useful to have, but it complicates insertion because then it's another point you got to worry about, right? So we will get to that. And then we wrapped up last time talking about binary search trees, BSTs for short. And that's when you have a certain kind of ordering to your trees where you put smaller things to the left, bigger things to the right, and you do that for everybody. And it's a global effect. And that lets you easily search for something in a quick way, assuming your tree is nice and balanced. You end up with logarithmic time, which is super nice. It ends up looking and acting just like binary search is and how you would expect it to be. So yeah, I think that's what I wanted to say. If we are good, let me steal this guy. And let's talk about inserting into a binary search tree, because we talked about searching, like going and finding something. We have an algorithm for that. Let's talk about inserting into a binary search tree next. All right, so let me get rid of the green stuff here. And then we shall draw. Because if you think about it, insertion is very, very tied to searching. Because like I was searching for example, back this time, I was searching for the 7 that didn't exist right here. And I got to null right there. And that's when I noticed that 7 node didn't exist. But you kind of see how, like, if I were inserting the 7 for the very first time, I would also end up right there. That's where it should be, where a search would have taken me. So searching and insertion are tied together very, very tightly, and that is very important. So let's talk about that. So if you want to insert into a binary search tree, we'll make this kind of function like insert into a tree node star reference, because potentially you're inserting the first thing and the root changes, right? If you're inserting the first thing, a new value. All right, so we'll get to that. But yeah, here's the setup. Do I want to do that one? No. I'll do that in a second. But let's say I've got this tree, and I would like to add, let's say, instead of searching and noticing that the 7 isn't there, let's insert a 7 node. Bless you. So let's try that. What would happen, right? I would like to, if I want to insert a 7 node into this binary search tree, you really just search it first, see if it's there or not, because usually if it's there, you don't overwrite it. You don't have duplicates in a binary search tree most times. You search to see where it would have gone. And so that's like, all right, 5, 7 is bigger, so I'll go right. 10, 7 is smaller, so I'll go left. Oh, there's nothing there. And then you notice, okay, that's where it would have been if it was there. I want to put it there now. All right, then you actually make the new node. You put it in the spot. So you have to remember who was above it, for example. So like you have to like keep track of where you just came from, because it's going to be the left child of that guy. It gets a little weird, but yeah, that new node that you make, if you think about it, it's going to be a leaf for sure. It's going to have no left or right children yet, because it's a brand new place in the tree. There's nothing underneath it. You're not going to put stuff underneath it until maybe another insertion. And then also, so you're going to set the left child of the 10, and then also the parent of the 7. If you're dealing with parent pointers, the parent of the new child is the place, like that node you just gave a child to, essentially. All right. So that's how that's going to work. And yeah, if you have we're going to, just like for linked lists, we're going to represent an empty tree with null. So like just a root pointer pointing nowhere at all, that means the tree was empty to begin with. Okay. Let's do that again with this kind of tree. So 7, 3, 42, and 4. Let's try to insert, I don't know, 5, something that would have gone there, right? Just to show that process again. So if I've got a root and that is legibly spelled, and we've got like a 7, and then a 3, and then a 42, and then a 4, and I've run out of room. Give me 1 second. Let's make this smaller, or at least move it up. Can I do that? Success. All right, so I've got this tree. I guess I can make that bigger now. And I want to put like the 5 node. I want to insert a 5. And so how will I do it? I will search for where it needs to go. I'll start my little pointer at the root, and I will search for, all right, if I want to insert a 5, smaller than 7, so I better go left, so I'll change n to here. It's bigger than 3, so I'll go right, so I'll change n to here. And then it's bigger than 4, so I'll go right? 5 is bigger than 4. So I'll try, and I'll notice that there's nothing there, and that's where I want to insert. Then I'll make my node. The devil's in the details, of course, but I'll make my 5 node. I'll set the right child pointer of the 4, the parent of the 5, doing all that fun stuff. All right, so that's the goal. Does it make sense on paper? The code's going to look a little weird. One important thing is this reference right here. I hope you can see why we need that. The very first time we have a tree, the root is pointing to nowhere at all. And we're going to make that first root in the tree, right? We're going to make the first node in the tree becomes the root. So we better take this tree node star root as a reference so that I can change like main's root variable. Because like that's the tree at that point. The very first time you insert, that thing is the root now, and you better change the root, okay? So you couldn't take it by just a copy, just like a pointer by itself, because that wouldn't have changed the original thing, okay? So we need that for our first insertion. So yeah, with that, let us go to code. I'll copy in last time's stuff. What did we call it? I think it was just .bsts, right? Lecture 16, bsts.cpp. So let's get that here. And let's add back in parent pointers. Star parent. And yeah, so we know how to search. Searching did not need parent pointers. We're just going down the tree only. But insertion, we want to do it right? So let's say I want to make this exact tree, 7, 3, 42, 4, 5. I hope you can see, like, if I first insert the 7, then the 3, then the 40, it's going to build the tree properly, right? If you do it by levels, then the 4, then the 5. Because if I inserted the 7 and then, like, the 5, then it would have gone, like, right here. Can you see that? So, like, you got to do it in an order. If you want to make this particular tree, there is an order that's involved. But level order is fine. 7, 3, 42, 4, 5. So let's insert those things. Let's pretend I have what I want to have. So I'm going to get rid of all this other tree stuff that we've made here. Be gone. And then what I'll do is I'll make a pointer to a root and mark it as there is nothing. The tree is empty right now. And then I'll make an insert function so that I can call it with the root of my tree, like insert into this tree, rooted here, the number 7, the key 7, the key 3, the key 42, the key 4, and then the key 5. Okay, so that should, if you do it in that order, is going to build that tree. Okay, so that's what's going to work, and then we'll print it out to make sure it works eventually. But let's do that. So I want to make this exact function: insert the key into a tree rooted somewhere called root, but it's a reference. Tree node star reference, because the very first time, right, root is null. If I didn't take a reference here, I would never be able to change this root in main away from null. Does that make sense? So that's important there. So that's why we take it as reference. It looks a little weird, okay? But yeah, let's make this happen. I'm inserting a brand new key in a brand new node. So the first step, I guess, could just be, let's make the node I need to insert. Let's just pretend that the user is always going to give me a node I've never seen before, so I know there's no duplicates. So I'm just going to make a brand new tree node on the heap right now, call it new node, new tree node, and I will make sure to do the right stuff to it. So I make the thing we're about to insert, set its key, of course. Here, this is what's involved in every tree node, right? You got data, left, right, parent. So let's set the data. We can immediately do that. That's the key value that was passed to us. So new node's data is that key value. And then this new node is for sure going to be a leaf, right? It's always going to be at the bottommost place of wherever we insert. There's no children yet for it. And so we're going to set the left and right null. We can just do that right now. We don't know who the parent is yet, though. So new node left equals the same as new node right equals null pointer. Okay, so it's a leaf. And I have no clue who the parent is right now. Just in case this is the first and only thing in the tree and it becomes the root, let's just set the parent right now to null. New node parent equals null. And if this happens to not be the root of the tree, we will set the parent properly later. But like this is just making sure that everybody's happy, everybody's declared and initialized. All right. So this may change. The very first time we insert, though, we're going to keep it that way. Okay. So we're going to have a couple cases. I hope you can see like that's the reason for this ampersand. There's going to be a special case where we just inserted the very first node in this tree. And then, so that means the root used to be null and now it's not. It becomes that new node that we just inserted. There was nothing, and now there is something, okay? So that's going to become the root in that case. So let's handle that first, maybe. So empty tree case. So if the root is empty, root is null pointer, that means there's nothing in the tree. I'm inserting the very first value, so that first value is going to become, that node is going to become the root, all right? So that means the new node is the new root. Yay, that's exciting. And so that means root equals new node, and that's pretty much it, because I've already set the parent. The parent of the root should be nothing, because there's nothing above it. The left and right are null. It is both a leaf and the root, all right? So I can just like return. I don't have to do anything else now. Does that make sense for the empty tree case? It's like that is the one and only thing. It is the root. We've set all the proper parent pointers and stuff. Everybody's happy. Okay, so that's the easiest case, I guess. Otherwise, we're in the general case where we have to search for where that node should be. Okay, so that's going to be the next step. So it's most of what we did before. We're going to copy and paste a whole lot of this searching stuff, but it's going to look a little different. Okay, so yeah, essentially, I do want to do this. I do want to do this searching game. It's going to be very similar to search. Let me copy and paste it, and I'll show you what needs to change. So if we're still here, if we did not return yet, that means we're in the general case where we have some value that we want to insert in this tree. Let us search for where it needs to go. All right, search for where this new node, this new keys value should be, and that's what I'm going to do. So while I can keep going, hopefully this will never break out of this loop. This is important to never break out of this loop, because the second you get to null, it's too late, right? You've gone past the node where you wanted to insert the thing. All right, so let's think about what needs to change here. So we're searching, right? We're searching, we're looking at n-arrow data and seeing if we need to go left or right. For example, I'm at the 5, and I'm like, oh, I want to insert the 7, so I will go right, because 7 is bigger than 5, and that will bring me here. And that is a valid node that could potentially have a child still, right? If there was nothing to the right of 5, then I need to stop, right? Because that's where the new thing should go. So I need to look ahead. I need to look to the place I'm trying to go down, just in case it's null, right? Because that's where I should insert. So there's it's a little bit, you have to think a little bit more than the searching case. It's not just go left, it's go left and see if there's something there. Can I actually go left and get a real node right now? Because otherwise that is the parent. Where I am is the parent. All right, so go left if we can. All right, so n equals n arrow left. If I can do that, that means if I have a valid node there that could potentially be a parent of somebody. So if n arrow left is not null, all right, that's the new thing. If there's an actual concrete node to the left, that's a better candidate for being the parent of this key I'm trying to insert. Does that make sense to us? It's further down the tree, it's a real node, I'm good, all right? If n arrow left is not null, I'm happy. So that's like I'm trying to insert, I don't know, 5, and I see 7, I can go to the left because that 3 node is there and it's not null, all right? But if I'm here, like if I was here before the 7 was inserted, if I'm at this 10, and I see, oh, I want to insert 7, it's to the left, I want to go left if I can, and that's n right now, right? This 10 could be n. N's left is null, so I can't go down that route. That is now the parent, right? That should be where I insert. That should be where I insert, and so that's my else case, okay? That's my else case. Now do the thing, all right? So else, that means it was null to the left. That means this is the parent, all right? This is where this thing should go. N's left, you were null, but that's where the new node should be. So n's left, hey, you're now the new node. Does that make sense? That's the trick, all right? So that's how we set up. We know we keep ourselves at n for a split second longer now than searching, and we know that, okay, this is my n, n's left was null, okay, now it's not, and then the only last thing, because like the left and right are correctly already set for 7 to be nothing. We just need to set the parent of 7 now. Set the parent of 7 to n. We have a hold on it now. Okay, so we're good. Parent of 7 of that new node is this n. All right, new node parent equals n, and that's, I've done the insertion. I do not have to continue this loop. I am done. Return. Does that make sense? Because it's going to be symmetric for the other side. Okay. Dun, dun, dun. So that's how that one can work. Otherwise, if the key was bigger, I want to go to the right if I can. Again, if we can. And so that's like if and our right exists, it's not equal to null, then keep going down. That's where's that? So that's like I'm at the 5, right? I'm trying to insert the 7. Oh, I want to go to the right because 7's bigger. There is something there, so I'll go. All right. That's that one, getting to the right. But if I ever get to like here, right? I'm at the 4, I want to insert the 5. 4 is my n. I notice that, oh, I want to go to the right, but there is nothing to the right now because the 5 has not yet been inserted, right? And our right is null. Therefore, okay, that n is now the parent of the 5. I'm going and inserting there. And our right, you were null otherwise. If it was null, then in our right, you're not null anymore. That's where the thing should go. So there I am, inserting the 5, all right? And then marking, the only other thing I need to do is mark that n is the parent of the 5. So this is, I'm sitting right here, just set that 5's parent is 4. All right, so n's, new node's parent equals n. So it's a symmetric, right? It's symmetric to this case, exactly the same. And then also, I don't need to search anymore. I am done. You could say break, I guess. To break out of the loop, I'll just say return because it's a void function. It's like done. I'm happy. Okay. So yeah, that is that's pretty much what I wanted to do. You can keep this else case if you want, because like what if usually BSTs they don't have duplicates. So if you searched and you just found the node itself, right? I found the node, that is the key that I wanted it to be there. Like I'm trying to insert this key. I already found it. Then we can just not insert it again. Just notice that, okay, found it. It's already in the tree, in the BST. So I can return, do nothing, but also I don't want to leak memory because I made this brand new node hoping to put it somewhere. So let's just delete that as well. Let me delete new node without having put it in the tree. Okay, so let's not leak memory. Yay. And so that's pretty much the insertion algorithm. It's a bit longer. Can I show it to you in one page? It's going to be a little small. Probably too small. Something like that. All right, any questions about what we've done? Do you see all the pieces fitting together? I think the loop is the key bit here. It's like that. Searching, but not quite, right? It's searching, but stop if you're going to hit null, because that is the place where we should insert. That's the new thing, okay? So yeah, let's watch it work, at least. The fruits of our labor. And I have not printed anything out in this program yet. Let's this should build, right? If we did it right, it should build this exact tree. Let's prove that to ourselves by making sure the root is 7. So see out roots data, because the root should have changed, right? Roots data. Let's print the roots. Print the 42. Roots rights data is 42. Start the root, go right, hit the 42. And then let's print that 5, right? Let's go. We've got, starting from there, how do we get to the 5? So it's roots, lefts, rights data. You see that? So roots, go left once, and then go right 3 times, or twice. Wait, left, right, 2 rights. Yeah, 1 left, 2 rights. Right, and then I'm there, get the data. I think. Do I get my things? Get my 7, get my 42, get my 5. So the root did change away from null pointer. Thank goodness for this reference right there. Nice. So yeah, I think that's the example. This may be a little weird and confusing. The algorithm is in your book. You'll be reading more about it if you have not yet already. but this is a good starter for all of this stuff. So definitely stare at this code for a while and ask me lots of questions when it's confusing. But I think that's all that I want to say for now about the algorithm. Are there any questions about it before I go to another slide? All right, it is fun though. It's so cool to watch it work. Let's do an analysis of insertion. It's going to be very similar, at least as far as time goes, to search, because it kind of depends on search, and search is kind of the bottleneck. So let's think about this. So, okay, space complexity first. That's usually the easier of the two. So space complexity is always how much data is being used or created inside of this function. You don't count the original tree. You think of this as like, that's just a pointer that was given to me. It's a variable, essentially. It's 8 bytes. The tree itself already exists, but what was given to me to call the function, that was like the pointer to the thing. And then 4 extra bytes for the key. And then it's just like I'm making a tree node. I know what a tree node is. It's not making just an arbitrary size thing. I know that a tree node is 3 pointers in an int always. That's a constant number of space added to the heap, right? And so that's constant space up there, constant space right there. And this n variable is just 1 pointer again. It's a constant sized thing, regardless of how deep that original tree was that I'm trying to insert in. Yes? So that means that space complexity is constant. All right, so just like search, it's constant. Even though I'm making it one thing, it's just because it's that one thing. Because I'm not making like a bunch of stuff. It's just one thing. So there's that. There's like a bug right here. What are you? Why? Ooh, it's flying. Okay. So yeah, that's space complexity. Let's do time complexity. Time complexity is okay. In the general case, I think you can imagine like constant time if it's the root we're trying to insert right now. But if we have to hit this loop, that's the bottleneck. So let's figure that out, because that's going to give us worst case time. So, okay, what we need to add is we need to search, right? That's the first process. Search to see where the thing could go, because you're going to hit null eventually in theory. You're going to get down potentially to the lowest level of the tree, right? Because say you wanted to insert, like you could, like your worst enemy could give you your insertion key right now, like insert 45 is going down to the lowest level in the tree right now. If you wanted to insert, and it's not that, I guess, like say this 42 wasn't here and you were inserting the 42, then it's easy, right? But you could pick a number that's bad, like 6, and bring it way down to here. Yeah. So that's, you could always get to the lowest level, and that means you're hitting the worst case time of search, which we know is O of H time. It's on the order of the height of the tree, right? Because you're moving down, doing constant work at each level, like doing some if statements, some nested if else's, going left or right. But if that's constant work per node you're looking at, you might have to look at height number of nodes, okay, to get to somewhere, to get to the parent. And then you have to create the new node itself and like move around some pointers, like all this stuff up here, that was constant, just to make the node set stuff. And then once you find where it needs to go, it's just a couple lines setting pointers some more. It's still constant time. All right, so per node you're looking at, and then when you do the insertion, it's all constant. And so it's really just search. It's O of H plus O of 1. So O of H total work. Searching was the hard part again. All right, does that make sense to us? Just like kind of search where it needs to go. Could go down to the height of the tree levels, and then add the node there once you find where it needs to be inserted. That's just constant time once you get there. Okay. I hope you can see that. Yeah, any questions about that before I give you a question? All right, here is your question. I guess let's go to the written ice page. I think that would be fun. Please fill that out. Do attendance as well. Yep. I will clear it. You can elect a leader. So say hello to the people sitting next to you, and please discuss this question. Let's say you've got these numbers. You want to make a binary search tree of these exact numbers, 1 through 9, only those. Which insertion order, because you can say what gets inserted first and second and third. Like you want to insert all these values. It doesn't have to be in this order, right? That's actually the worst possible order to do the insertion. I hope you can see that. What insertion order makes like the most balanced binary search tree? There's not just one answer, but I want you to think about this, right? Because kind of like draw the picture. This will get you practice with insertion and the algorithm on paper. I think that would be a great idea. Okay, so questions about the question? Take out paint, take out a piece of paper, and tell me, like, what's the best order you think that you could add these nodes into this tree? Like pull insert this many times on a blank tree. What's going to get you an isolated one? What's your next thing? So first, you draw the tree and you'll be like, another minute or so to discuss, then we'll come back. All right, that was my timer. Did we decide? Did we decide on a good order? Give me another few seconds to type something up. You have not pressed submit already. Yeah, let's take a look. What's the best order? Random order, technically, that would, on average, a random order should do it right? That's great. But it looks like a lot of us think that, all right, 5 is the best number to insert. Then not 1 or not 9 next. Something like that. It looks like we seem to have similar ideas, and let's try to get at that. So nice, very nice. Let's take a look. Thank you for this. So let's see here. We know that the worst order would be in ascending or descending order, yes? Yeah. Because it would look like this. You insert the 1, oh, that's the root now, right? Because that's what the algorithm does. Insert the 2, it's got to go to the right of 1. Insert the 3, it's got to go to the right of 2. See that? 4, going there, 5. It's a linked list at this point. Yeah? That's unfortunate. For similar reasons, even if you do the rest of this balanced, it's a horrible idea to insert the 1 first to the 9 first. Even if you do a random, like nice and balanced order for everybody else, like you do as balanced as you could for everybody else, because it's going to be leaning, right? There's going to be nothing to the left of 1. Same for the 9. There's going to be nothing to the right of 9. even if you balance the rest. So with that in mind, I think 5 is probably the best one to do first, because it kind of splits everybody, right? It splits this half and this half. And then you kind of want to play the same game for those smaller halves, yeah? So then you want to insert these guys in a similar way, where like you insert the middle first, where there is no middle of an even numbered stuff. So like you got to pick 2 or 3. You're going to get a symmetric looking. It's not going to be perfectly balanced at that point, but you did your best, right? So let's just arbitrarily pick 2 rather than 3. And then we'll insert, well, the 1's kind of forced now. And then we got the 3 or the 4 next. It doesn't really matter. It's going to get to be this deep. Something like that. You could have done 4, 3. 4, 3 would look like this. It would be just as balanced. Either way. Okay. I'll do 3, 4. Makes more sense to my brain. And then for similar reasons, all right, 6, 7, 8, 9, you can insert the 7 or 8, like the middleest bit of it. You just keep doing that game of, you got a smaller number of things, you insert in the middle of that. Which is kind of interesting because that sounds like a recursive algorithm when I think about it. Right, I'm breaking things down, I'm going in the middle. Interesting. That is also where we're going. So, okay, maybe I'll insert the 8, and then like then the 9 is forced to go right there whenever I choose to insert, and then 6 and 7. I could do it in anywhere. I could do 7, then 6, or I could do 6 and 7. Either way, that would look like this, but that's decently balanced. Okay, so I hope you see that there's an algorithm there hidden away. Okay, any questions about that? That's how you can get as balanced as possible. You want to take the middle. Then you got two new sides. Take the middle of those. Keep playing that game. So I think that would give you the most balanced thing. So yeah, I think that's most of what I wanted to say for our introduction to binary search trees. We're going to have a whole set of slides on binary search trees. They're very important. But are we ready for something slightly different, but still tree-based? All right. Because where I want to go next is I would like to do recursion on trees. Why not? If you go left on a tree, you have another tree, right? You got a subtree. It's a little bit smaller. Just consider everything but that first node. Like if I go left on this tree, I've got a smaller tree right there, don't I? If I consider it as rooted at 2. It's a smaller tree, so I can do recursion on it. Just like if I had a linked list and I went to the right, I went to the next thing, I have now a smaller list to look at. For the same reason, I can do recursion on trees, and there are some popular recursive algorithms that like go to every node. It's called a traversal of a tree. We'll talk about those as well. So yeah, let's get there. All right. So yeah, like recursion is going to be the answer to this question. Like, what are the different ways of like moving around a tree? Like, I want to go to every element. I want to do a computation per element of this tree. How can I make sure to get around? Because it's not just a while loop anymore very easily, right? There's not like, while I'm not done, go to the next thing. Because like you could go left or right now, yeah? You got to go both places. And so you could use a queue or a stack, but you're kind of simulating recursion at that point, so we're just going to go straight there, right? That's how we're going to iterate through a tree. We're going to do it recursively. That's the easiest way, all right? So recursion on trees is when you run your little problem on a smaller tree inside of the original tree. So if I had this tree, here's my root. It's, let's say, a 7 node. 7. Let's just draw a binary search tree. It does not have to be a binary search tree. It's just a tree at this point, left and right pointers. But we understand those now. Maybe 10 here. That's the original tree, but you can make smaller trees. You can find subtrees of these trees, right? So here is, if I go left from the root, I have this entire tree to look at, right? I have that one. If I go right from the root, I have this entire tree, because trees are represented by pointers to their roots. If I go left from the root, I have a pointer to right there. Consider that as the root of another tree. Yeah, it's a subtree at that point. So that means I have a smaller tree that I could perform my computation on. I have 2 smaller trees that I could perform my computation on, because it's smaller due to the magic of recursion. Just have to make that leap of faith. You can make a recursive call down these subtrees and assume you get the right answer, as long as you build up the answer correctly using the one thing you have not yet considered. Just like when we were breaking down lists. You go use the smaller tree, do the thing, consider that node you have not yet considered the start of the tree, the first thing. Or sorry, the start of the list. So we can make a recursive call right there. And on the right, you can make a recursive call right here. Boop, just like that. And everywhere else. And if you keep playing that game, you keep going left, keep going right, call yourself recursively on these subtrees, like you'll eventually get down to here, like those are recursive calls. You can notice when you're out of leaf, and that could be a base case, or you can just let the base case go down to the leaves. Just like, all right, go left, go right. When you see null, do nothing. Just like when you saw null for a list recursively, do nothing. There's nothing there. So same with all that. You go left of the 8, nothing there. Go right. We got the 10 node as a whole tree, a tree that is its own root, right? Just one node, left and right, left and right. You'll hit all those places with recursion, and then you build up the answer bigger and bigger once you get down to the base case and start working your way back towards the original call. So that's kind of how that's going to work. Do you see what might eventually happen? Right? You see the smaller trees. Any questions about picking that out? You see how it's very similar to linked lists, and you find the smaller linked list? Because now I'm ready to give you some examples. I'm very excited. So I will, on paper, give you this idea, because this is going to be part of a future lab. So let's say I've got a tree, and the keys in that tree are numbers. So I've got this tree again. Let's say it was 7, 5, 8, 3, 6, and then a 10 over here. We can totally make a recursive function that calculates the sum of all the nodes in this tree. Think about it. So here's my root. That's what you start with. You give, it's called the sum function on the root of the tree. Here is the root. Here's the recursive case and the base case on paper. You're going to implement this yourself, so you have to translate it. All right. But I will draw many pictures so that you get it. But let's say, all right, you got this tree. You know that you can make a recursive call down here to this subtree, like go roots left, call sum on roots left. Yeah. Call sum on roots right, because that's how you represent that tree, by the pointer to its root. Give me a pointer to that thing right there. That's now a new tree. All right. You get to assume that the recursion is going to correctly give you back the sum of those smaller trees, don't you? So, all right, you know that you're getting handed to you on a silver platter the numbers 14 and 18. How do you build up the original tree's sum using those? That's all you need to do at this point to correctly have a recursive case. You just have to consider your 7, right? That's the one thing that has not been seen yet. So your result in the recursive case, after you sum the left subtree and the right subtree recursively, you add your current node at the root of u, right? So root's data, wherever you are right now. So that's 14 plus 18 plus 7, whatever that is, that's your answer in the recursive case. Does that make sense? You have to believe in the recursion, and I'll prove to you why it will work, but that's the recursive case. You only need a base case now. As long as you do the right thing there too, you're good. The base case for trees can be very similar usually to the base case for linked lists. So sometimes you want to stop when it's just the one node. That's the only thing left. Sometimes you can just stop when it's empty. This is a good place to stop when it's empty. If you have an empty tree, what is the sum of all the nodes in an empty tree? 0. So just like, all right, if my root pointer is null, give back 0. I'm done. That's quite nice. Does that make sense? Those two things working together? I still need to prove to you that it'll work, but hopefully you can feel it in your bones. So here's the tree. Let's draw it. So I've got this tree. Let me draw what's kind of going to happen on the stack in a weird way. It's going to be a tree diagram rather than a stack diagram, because you have to make 2 recursive calls, but we'll get there. All right. So here's why this is going to work if you do it this way. Here's why. We'll get down to the base cases and do the right thing. So like originally you're going to say, hey, give me the sum of all the nodes in this particular tree rooted there at the 7. You're going to say that. So, okay, 7, 5, 8, 3, 6, 10. So it's like, this is how I'm going to draw this call. So I called the function with this tree. There's the call, the original sum call, all right? And then what you're going to do is you're going to break it down into 2 calls, right? You're going to call on this subtree and this subtree sum again, right? That's the recursive case's job. Go down the left and the right subtrees, smaller trees within the bigger tree, and do the summing. All right, so you're going to make a call over here, give this tree to sum by passing a pointer to where it begins, to its start, right? And then also give this tree to sum, 8 and 10. Does that make sense? These are the 2 recursive calls that this function will do. I'm drawing boxes around them to show the tree that's being passed. Does that make sense? So that's what's happening there. And again, you're in the recursive case for both of these calls. This one's going to finish first, of course, but like we can do them at the same time. It doesn't really matter. So yeah, you're going to go down. This is not a null tree, right? It's not empty. So you're going to do on this side and this side. You're going to make a recursive call to, hey, sum of every node in the tree with 3, rooted at 3, and the tree rooted at 6. And there's nothing underneath either of those, right? Null and null to the left and to the right. So when you make this call, again, you're not in the base case. It's still something is there. You still have a concrete node. It's not null yet. It's not empty. So you're going to go down both halves. All right. I'm going to make a recursive call down the left subtree to get to nowhere and the right subtree to get to nowhere. And those are my base cases. All right. So it's like you're here. What is the sum of all the nodes in this tree? Well, it's the sum of the left subtree plus the sum of the right subtree recursively. Those answers hit the base case, and we get back 0 from those calls. Yes? We're getting back 0 from those calls. We just have to consider our own rooted node at our root, because from this tree's perspective, root is that, right? That's your parameter, its name or whatever. Add the 3 to that, and that's your final answer. 0 plus 3 is 3. Give that back. That is the correct sum of that, all the nodes in that tree. Yeah? For the same reason, you're going to get your way down to both sides of the 6 and give back 6 after hitting 0 a couple times. And then now you're here, right? You did the right thing from the left side. You got 3 back over here from this recursive call, 6 back from this recursive call. You just need to add those 2 to your 5, and that makes 14, and you give that back. That's the recursive case working. Does that make sense? How it's going to build up that answer. You got down to the base case, work your way back. It really will work. Okay, for the same reason, this one, you got nothing to the left of 8, but you're going to make that call anyway. It's like, all right, go down, sum up the left subtree and the right subtree. So the right subtree is just the node with 10 in it, which will eventually, well, this one's a base case, gives back 0. This one will eventually hit base cases and give back 10, 0 plus 10. So that's that one. And then, all right, we got 0, we got 10, add an 8. That's the recursive case's solution, always. Give back 18. Now we're back in the original call. Everybody's happy. The left subtree's recursive call completed. Same with the right. We got 14, we got 18. Add those 2 with the 7. Give that back. So this one's answer is 14 plus 18 plus 7. I'm too lazy to do the math. But that's why it's going to work. Does that make sense? Just at a high level, at least. Like you make those calls, it will get down to the base cases. As long as you do everything else right, you are set. You are set. So this is something you're going to implement. So I'm not going to give you the actual code, but I'm going to give you code for future recursive algorithms. Okay? Any questions about this one, though? Sum of all the nodes. Do you see how easy that is? Like, once you get past the recursion, it's like, oh yeah, that's an easy way to go everywhere and do something. That's lovely. That's you iterating through the tree without a loop. Looping with the recursion. All right. Do I want to do that one? I do. All right. So here, the next one I want to do is called a traversal. So this is just, technically, this summing function did a traversal. It visited every node. The word for visiting every node and going around a tree is called a traversal. I'm traversing through the tree. It's like you're on an expedition. So there are particular words that describe the way you went around the tree. If you think about, go back to, once I teach you all the words, go back to the sum case and figure out which one it was. But one of the ways to go about a tree is in order. Some people, we're just going to use one big word to mean that. That's what most people say. This is an in-order traversal, right? This implies the existence of other kinds of orders. There is a pre-order, there is a post-order, and there is an in-order. All right? Those are the 3 I'm going to teach you. And what the prefix here means, the pre, the post, the in, it means when you consider, because it's all going to be recursive, all these different words, what this is referencing is when do you visit your root of your current subtree? When do you look at that? Do you look at it first? Do you look at it last? Do you look at it in the middle of the 2 recursive calls? So that's where we're going. All right, so just keep that in the back of your mind if you can remember that. But an in-order traversal is one of the many ways of going through all the nodes in a tree, visiting each of the nodes this one goes in order if it's a BST. If it's a binary search tree, it'll go in order, and I'll show you why. All right. So an in-order traversal goes in order through all the elements of a tree. And this visiting, that's a vague thing, right? Because maybe visit means sum up. Let's pretend we essentially did a traversal for summing. But let's say that visit means print for us right now. Just print out all the nodes in the order that we visit them. Okay, so this is kind of like the job of an iterator. That's kind of cool. All of these traversals are essentially iterating through a tree. This one will be part of your lab, but I'm going to give it to you anyway. So let's say, again, we've got this tree. I'm going to need it a few times, so maybe I should copy and paste it. Yeah, let me put this tree everywhere it needs to be. So I've got, what was it? My favorite tree for this this section is 7, 5, 8, 3, 6, and 10. So I've got all those guys, and I'm going to do this for a bunch of examples. So let me get that ready. So that one, I'm going to need it for this one probably. Yeah. I'm going to need it for this one. Actually, no. I'm going to need it for this one. That one. I think we're pretty much good. Depth of there as well. All right. So I put it everywhere. I'm going to make a drawing. Okay. We're ready now. So, okay. I would like to go through and visit all the nodes, if it's a BST at least, in order. So I want to print out all the nodes in this order. I want to go 3, 5, 6 in sorted order. 7, 8, 10. All right. And you know that we're going to do this recursive. So I'm going to make recursive calls. I'm going to go down the left subtree and the right subtree. And I get to assume that when I do that, I will get out those nodes printed in order. Yeah. So where are the recursive calls happening here? Well, there's one there, and there's one there. Does that make sense? You see it? So if I go down, if I do an in-order traversal of the left subtree, print my 7, and do an in-order traversal of the right subtree, that is the order. Yeah? Does that make sense to everybody? Because this smaller subtree, you just get to assume, you just like hand it off to yourself. It'll do it. So like you make the call, you've done that already. You make this call, you've done that already. The details involve the order now. Like where does the 7 go? It's in the middle. That's why it's called in order. Okay? That's an in order traversal. You have other options, but that's that one. All right? So that's your recursive case. Assume that it's going to do the right thing for the subtree. So you're going to go down the left subtree. So you're going to recurse down the left subtree. That's the verb form of recursion. Recurse left, print your root, and then recurse right. That will give you this ordering. Because the 7's smack in the middle there. Okay? So again, I'll code that. This time I will code it and show you why, but that's that one. And yeah, for the base case, again, you can do nothing because it's nice. You got an empty tree. You want to print all the nodes in that? I'm done, right? That's easy. So, okay. With that in mind, let me draw a picture of why this is going to do the right thing. So I've got my 7, 7, 5, 8, 3, 6, 10. So there they are. So let's say I want to do an in-order traversal of this tree. What will happen? So I'm going to draw like what's being printed down here. So the very first thing I do is I recurse left in the recursive case. I want to make a recursive call down the left subtree. So I'm going to recursively in order this guy. That tree is the next thing I'm going to pass. So in order, before I do anything at all, that's the first step. In order traversal of 5, 3, 6. Okay? So there we are. And again, this is a recursive case. So to do this one, it's an inner traversal of 3, right? It's going to go recurse left, print the root, recurse right. So first is 3. All right. So this is going to recurse down the left subtree, 3. And then, all right, I'm at this node, but we know that's it's still not empty, right? It's got null left and right children. And so it's going to, okay, the first thing it's going to do here in the recursive case still is recurse left, print the root, recurse right. So recurse left, go down the null tree, emptiness, do nothing, it returns, right? Print the root, so 3 is the first thing being printed correctly, and then recurse right. So we're going to go down the subtree again, do nothing at all. And then we're done printing this tree. Does that Kind of makes sense how that's happening. And that was like all because we wanted to do this one, right? It was recurse left, print our root, recurse right. So now we're ready for our root, right? We're ready for the root time. So now we can print the 5 from this one's perspective. And then we recurse right, go down this subtree in order traversal of the 6 node, the tree rooted there. And so again, it's left, root, right. So left, root means print the 6. Right means go down there. It's the base case, do nothing. And so I have correctly completed now that recursive call. I've got my 3, 5, and 6 printed to the terminal. Does that make sense? In order traversal. If it's actually in numerical order if it's a binary search tree, because these things could have been just a normal tree. And it would be a little jumbled if that was the case. All right, and then we got this side, right? Oh, wait, no, sorry, excuse me. This one, from this one's perspective, it was going left, recursive, root, right. So now it's root's turn of the original recursive call. So now we print our 7. And then we recurse right? It's always that for an in-order traversal. That's where it's the printing of the root is in between. So it's recurse left, print the root, recurse right. All right, you will get used to this, I promise. So now it's time to recurse right. So we're going to make a call to in order on that tree, 8, 10. And again, it's not empty. So left, root, right. Recurse left means go down the empty tree. So there's nothing over there, right? Print the root, 8. Recurse right, so now go down this tree. The tree rooted there, which has null left and right children, which is going to do the left, root, right again. So like recurse left, all right, we're going to make this call. Print our root, that's 10. Recurse right. Again, we hit the base case, we do nothing. So now this one's done, which means now this one's done because it did the left, root, right. We were in the right, we finished that. And that also means that this one's done. Did the left, printed its root, it went down the right. The right side's recursion is completed now. And it gives us order. Isn't that cute? Any questions about that? So I'm going to code this now, if we're ready. All right, so lovely. We get sorted order if it's a BST at least. So let's turn this into code, and I'll show you how. I will make a new file for the recursion stuff. Tree recursion.cpp. So we've got all these nice things. Let's keep them here. Let's make the tree that I've been drawing, though. So to make this particular tree, I can, the easiest way is just to insert in level order. Like first the 7, because that forces the 7 at the root, then the 5, the 8, and then I can do the 3, 6, and 10. So 7, 5, 8, 3, 6, and 10. If I do it in that order, it will build this tree. Okay, so I have this tree now. Let's do, do I want to, let's see, so, so some I didn't do, I promise I'm not going to do that one for you, but in order I will for fun, all right? So I'm going to do an in order traversal of this tree, so in order on the root, and then let's go from there. So in order, what does that look like? It's going to be this kind of function. We've got this void, it just does something. So in order, and it takes which node you're trying to go down. So like what's the root of the tree that you want to print in order? It's always going to get a smaller tree, but it's still like, it's the root of that smaller tree now that you're passing. So it's always called root. It's the root of the tree you're considering right now. And so now let's implement. All right. So we've got the base case or the recursive case that we're in. We have to figure out which one, right? It's one or the other. So we know that we're in the base case if the root is null. That means the tree is empty and we can do nothing at all. So base case, empty tree, do nothing. That's easy. So you could have just made an if statement that was like, if the root's not null, we'll do something. But I'll just make an empty body there. Otherwise, I'm in the recursive case. It's recurse left, print root, recurse right. Recurse left, print roots data, and then recurse right. All right. So what does that mean? I'm going to call myself in order, do an in order traversal, please, in order traversal on the left subtree, and I pass that to this function. How do you pass a tree? It's always give me a pointer to the root of that tree you're trying to consider right now. So roots left. Does that make sense? That is a pointer to the left subtree. That is a pointer to right there. Does that make sense? And so now from that call's perspective, that's the root of the tree. Okay? And that's the tree it's looking at. So that's that one. To print the roots data, we know how to do that, of course. That's cout, just roots data. And then let's do it all in one line, so I'll do some spaces. And then recurse right just means, all right, do an in order traversal on the right subtree, and we're going to, the way we represent subtrees, or trees in general, is we pass a pointer to the root of that tree. So roots right is holding this pointer, a pointer to right there in memory. That's the new subtree that I want to consider. Rooted there, do something. Okay? And that becomes the algorithm. Does that make sense? How we read it off? That's what it turns into. And so when I call it, well, I guess I'm going to have to do, if I'm just doing it all on one line, I have to break that line down there. I'm calling it there. I better get those numbers in order. Look at me. 3, 5, 6, 7, 8, 10. Lovely. And so this code on the tree that we drew is doing the right thing. We drew a picture of why it's going to do the right thing. So I think that's the best that I can give you right now. Are there any questions about this algorithm? It's an in-order traversal. Left, root, right. So that's one way to visit all the nodes. If you wanted to do something special at that node in this ordering, like you just instead of printing, you do something else right there. Use the data now to do your thing. Does that make sense? Whenever you want it. But for us, let's just pretend visiting means printing. But you can change that, of course. All right? So yeah, if we're good, yell at me if you have any questions, but I just want to show the other two. So there's an in order, there's a pre-order, there's a post-order, and what this prefix means is that's the order in which you consider your root. So pre-order is root, left, right. Post-order is left, right, root. I'll show you both. So let's see. I don't really think I have to code it for you because you can kind of see it, but we'll draw what the difference is going to be now. So yeah, pre-order is, let's see, how do I want to do this? It's always saying, in which order do you visit the root? So this one means the root is visited first. Root, then recurse left, then recurse right. The root is visited first. And then for this one, the root is visited last. Okay, so that's how that one's going to work. And yeah, I think that's most of what I wanted to say. So let's do pre-order, of course, first. What is going to happen? I guess, first of all, let's see. Do I want to talk about this first or next? Let's just run the algorithm, and I'll get back to that first bullet. But that's an interesting idea. Okay, so let's run it. So it's going to be root from the base case is still do nothing for the empty tree. It's root, recurse left, recurse right, root, left, right. So what will happen to this tree? How will it be printed out in a pre-order style? Well, root first, so that's 7, right? I'll do a different color maybe for that. So 7, and then so that's the root. And then recurse left, recurse right. So when I recurse left, again, it's root, left, right, and the base cases will be hit for those small. I think you can imagine it's going to go 5, 3, 6. Okay. 5, 3, 6. So it's root, left, right. And when you get to this one, again, it's root, left, right, but the left and rights do nothing. So it's just 5, 3, 6 for that left call of that original left subtree. So it's 7. So that's the root. There's the left. And then for the right, again, it's going to go root, left, right, and so on. So that's going to go 8, 10. Does that make enough sense? That's the order you're getting back. It's a weird looking order, but there are reasons why you might want to do that. All right. So a good reason to want to do a pre-order traversal is for this. If you can make a tree of some tasks that you need to get done, and the edges along your tree right? Those are the lines, these pointers. They're also called edges. They separate nodes. They're like indicating requirements. Then a pre-ordered traversal is going to give you a way, just some way. You could have gone left or right, I guess. You could have switched those and it wouldn't really matter. But a pre-ordered traversal is going to give you an order in which you can do the tasks where one thing has to happen before the other. So for example, a good example of that is, that bug needs to stop coming near me. A very good example would be classes in the computer science degree here. So like you first have to take 40. That's the root of a tree, yeah? Then you must take 41 afterwards, and then that opens up 26 or 45. You can take those in either order. But a pre-ordered traversal will give you a way to take these classes. Does that kind of make sense? So you always need to do the ones above, the ones before their children. You can represent stuff that way. That's kind of neat. And so a pre-ordered traversal of this tree would give us root, got to start with 40. Root left, there's nothing left. And then right, okay, now do this tree, which is again root 41. Left, right was 26, 45. And that is the recommended order that we hope you take those classes in. Yay. Are there any questions about that? That's a pre-ordered traversal. It's for a different kind of tree. All right. Are we ready for post order? I think you can imagine that's useful for its own reasons. So pre-orders, root first. In orders, root in the middle. Post order is root last. Recurse left, recurse right, visit root. Okay? So I have a fun full circle example now. Dun, dun, dun. Do you remember when we were doing that calculator for reverse Polish notation when we were doing stacks? A post-order traversal of a tree that represents a mathematical computation, a post-order traversal will turn it into reverse Polish notation, which is very interesting. And I want to show that to you. So let's say I want to do this computation. 10 minus 3 plus 5, all that times 2. It's like that, parenthesized like that. If you were a compiler, or like you're typing this on your calculator, it's going to turn this into an expression tree, where like what happens first is very explicit. So like, what is the outermost computation here? The minus, right? 10 minus whatever all this is. So that's going to get turned into something like this. So you've got a minus, and then on the left, you got the 10, and then you've got this computation over here. What's the next outermost thing? Well, that's the multiplication, right? You're multiplying this guy by this guy. Do you kind of see how math can be turned into a tree? Where you don't need parentheses anymore. It's unambiguous what happens first. This is now the outermost operation, the multiplication of the 3 plus 5 and the 2. All right, so the 2's on the right, we know for sure. And then the 3 plus 5, well, that's a plus on 3 and 5. So the plus goes there, and then the 3 goes here, and the 5. Does that make sense? How this is like, that's the math. That's the same thing. You don't need parentheses anymore because like the way that the tree is arranged has ordered what happens first. Does everybody see that? If you want an answer, like, all right, I got to subtract this, all this from whatever's on the left. So I need to go get this answer, which is going to involve doing 3 plus 5. It's going to do 2 and then multiply them once you got the answers on the left and the right. So you kind of make your way to the bottom and build it back up. It's a little bit recursive, right? So that's kind of cool. That's what it will turn into. And if we have this tree, we can turn this into reverse Polish notation, which is another ordering form that does not require parentheses to be used by our little calculator app, which is wonderful. So here, what is post order? It's left, right, root. So left, right, root for this outer tree. So the left is going to go to 10, right? Which is, I mean, it's not yet the base case, you can imagine, but it's going to go left, right, root. There's nothing to the left or the right. It'll just do nothing. It'll print the 10 first. So 10. So left, right, root. So that we're now on the right. Okay? So we did this one. Left, right, root. Ta-da. And now we're going to do the right, right? Because it's from this tree, right? Left, right, root. So the minus is very last. It's dead last. So now this tree. So now we're going to do left, right, root again. So left, right, root. So now we're in this recursive call. We're going to do left, right, root again. So 3, which is going to itself do left, right, root. We're going to print the 3 eventually. 3, left, right, 5, root is the plus. Plus. And so we did this one. Left, right root of that one. Now we're on this one still. It was left, right root. It's going to get a little ugly. Left, right. That's going to eventually end up with 2, right? Because it'll do left, right root. And then, all right, that was this one still. It was left, right. Now we're finally ready for the root star. Because it's kind of, you need the results of the inner child trees, right? The inner subtrees before you can do that multiplication. That's kind of what it's encoding. That's so cool. So you have those left, right, root for the outer one, minus. And you better believe that's reverse Polish notation for that expression. So put the 10 on the stack. The 3 plus 5 will happen right there. Because 3, 5 plus pops the things off, gets the answer. 2 times going to take those things, whatever this answer was, and 2 multiply them together. And then the minus will take off this 10 and whatever this whole answer was and give you the thing. That's lovely. That's powerful. And so that's another way to represent things. Yeah. That need to happen. So that's pretty cool. That's an example of post order and a reason you might want to do it. There are other reasons. But yeah, you kind of see the differences of all those. Just the order in which you visit the root changes stuff. And there's reasons for wanting to do it differently. Any questions about post order? Because that's kind of the trifecta. You got in order, pre-order, and post order. Those are ways to visit the tree in some order. All the nodes in the tree you're gonna get to them eventually in some order, and the problem at hand depends. All right, depends on what you need. So I think that's what I wanted to say for that one. We still good? Ready for more? So yeah, I hope we're getting more comfortable with recursion, because that's another big thing that I want to make sure you're happy with in this class. Here is a wild card. This algorithm is not recursive. It's another kind of traversal, but we cannot use recursion in any normal way to do this one. So what we're going to use is a queue data structure. It's very interesting. What breadth first does is it's going to give us back the nodes in level order. This is what we want. Because you might want this one day. It's very useful to have this, right? I want 7, 5, 8, 3, 6, 10. Yeah? That's what I like. 7, 5, 8, 3, 6, 10. I want to go that way. Boop, boop, just like that. So that's the order I want to get things back out in. 7, 5, 8, oops. 3, 6, 10. So I want those things. And the way that you get there is to use a loop and a queue. It's very interesting. So here's the algorithm. You're going to make a queue, and you're going to push the root node, the 7 node, because the 7 has access to its children, of course. That's how you get to the 5 and the 8 eventually. But it's like, here's the algorithm. While the queue isn't empty, you take the thing that's in front, you pop it off, you look at it, visit it in whatever way you want to visit it. Maybe that just means print it. And then you push, at that time, its children onto the queue. By doing that, you're going to end up with level order. Because all these things, like the 5 is going to be visited before the 8, which means the 5 is going to push its children before the 8 pushes its children. I hope you kind of see that. That's what's going to happen. Okay? So let me draw that for you. It's a very fun little example. So the algorithm is, you make a queue and you push the root node to the queue. It's the node itself. You're going to push the tree node star. You're not going to push the number 7 because you've lost access to the 5 and the 8 nodes at that point, right? You're going to push the node itself. So I'm going to draw like, here's my queue of things. Starts out empty. I'm going to push the 7 node into the queue, not the number 7. So I'll do it like this, 7 with a circle around it. The node itself, the tree node star, so I can get at the left and the right still, right? So I need those things. And then I'm going to run my little algorithm. While the queue's not empty, it's not empty. I have one thing in it right now. Take out the thing in the front and visit it. So I'm going to get the thing out of the queue. Get the 7 out, visit it. The queue's empty right now. So visit it, print the 7, sure. Then you'll push the children of that node onto the queue as nodes. So you'll push the 5 and the 8 nodes onto the queue now in that order. Push the left node, push the right node. Okay? Now the queue looks like that. Does that make sense? So now we've got the children in order, and you better believe when I visit the 5, I'm going to push the 3 and the 6, and that will appear over here. Still need to get to the 8. That will give you level order. So, okay, then I'm gonna, all right, the next round, I'm going to pop the 5 off, visit the 5 by printing its values, and then pushing its children, the 3 and the 6, right? So the queue turns into this. Still have the 8. We're going to push the 3 node, push the 6 node. Okay? Does that make sense so far? Questions? So that's the algorithm still. So while the queue's empty, pop the front thing, visit the thing, push the children. So now I've got this queue. 8's at the front. I'll pop the 8, visit the 8, push its children. I got just the 10 node, right? So I've got 3 and 6 still waiting. And then I got the 10 next. And you see, just by queue ordering, I'm going to get to everybody. Okay? And so at that point, I'm going to pop the 3, visit the 3, push its children. There are none. Same for the 6. Same for the 10, because they're leaves. And that gave me all those guys in level order. Isn't that lovely? Yeah. So yeah, just be careful, because eventually I'm going to force you to implement this. You're not making a queue of ints. You're making a queue of tree node stars. Does that make sense? So you need access to your left and right children. It's the node themselves that has that. You need all that stuff together. So it's the circles, not just the numbers. Okay? Yeah, I think that's what I wanted to say. Where is that example? That's the last one. Okay. So yeah, that's a fun one. It's not recursive. Yeah, are we ready for a little bit more? Is that good enough for now? Because now we need to analyze this. And you know that it's a little disgusting when you're analyzing recursive stuff. So, okay. For time complexity, it's always like there's n nodes in the tree. Pretend there's n nodes in the tree. What do we got to do for all these kinds of traversals? Let's do the time complexity of these traversals. In order, post order, pre-order. All these guys. We've got n nodes in the tree. And like here's in order, for example. We've got n nodes in the tree. We're going to visit them all eventually. We're going to print their data right there. Like that's what's happening for each node, right? And each of these calls eventually gets to everybody somehow. Like here's the real work, though, that's happening per node. All the rest is just finding the way to the next ones, right? So, okay, there's n nodes in the tree. Every traversal is going to visit all of them and is going to do something at that node, assuming we do like printing, right? Our printing process, that's constant time. So like let's pretend it's constant time, at least for our examples. It does constant work at them, assuming you're just printing. So with that in mind, you don't really have to worry about the recursion too much. You can kind of just, I mean, it's high level, it's hand wavy, but I hope you can see that, all right, this is essentially what's being called, and just like I'm moving around to get there. This is happening as a constant time thing, and it's happening at every node, therefore linear time. Does that kind of make sense? I'm visiting every node, I'm doing that at it, and I'm just moving around to get there. These function calls will get down and eventually visit, like this is visiting in over 2 nodes if it's balanced, right? So visit in over 2 nodes, so visit in over 2 nodes. This is the extra thing. Adds up to linear time. So that's kind of what's happening. How do I want to say that? Right, you're eventually getting to everybody, okay? You're eventually getting to everybody. How do I want, I think that is correct to say. So yeah, that's kind of how I want you to think about it. All right, for the time complexity, at least there's n nodes. You're visiting all of them eventually, somehow. Okay, the space complexity is actually the hard thing for analysis of recursive algorithms, because you have to worry about the stack. That is disgusting. All right, so remember when you're making recursive calls, here's main. You're originally making a call to like the root of the tree. Like, all right, root of the tree. And then you're going down left or right. Maybe you're going left, left, left a bunch of times until you hit a base case, right? Each of these calls on the stack takes up space. Doesn't it? It needs to remember like the parameters. What's the root of this tree right now? Who do I return back to? So the question now is, all right, in the worst case, how high does this stack get? How many nested calls do I need to get down to the base case? Because that's what recursion's doing, right? It's keeping on calling its recursive case until it gets down to the base case. The worst case is when the tree is made in a very disgusting way, when the tree is secretly a linked list, when it looks like this. Do you see that? Because you're going to hit the base case way down here, having visited every other node along the way. Like all those are sitting on the stack right now. That's when the height of the tree is proportional to the number of nodes. Height is pretty much n. It's O of n. That's disgusting. That means the stack is going to be the height of the tree high. This is about h, right? In the worst case, like you got to get down to the lowest leaf, so you have to have that much room in memory to make that many calls at most. And in the worst case, your tree is disgusting. It looks like this. And the number of nodes is like going to end up influencing your height in that case. Does that make sense? So if the tree's secretly list, the stack's going to be that high because you got to make your way down to right here, and everybody else is waiting on the stack, disgustingly. And so you're holding just like pointers and stuff at each call if you're doing like constant work and normal things like we've been doing. That means you have linear space complexity in the worst case. You might have all n nodes, a call to all n nodes, and then the null pointer at the very end, +1, sitting on the stack. Does that make sense? Those calls all together. They're not finished. Questions about that? Because that's a little odd, right? But that's how it works. Like you have to keep calling this as long as you can. You're going to keep going left until you hit something. You're going to keep going right until you hit something. Like you might be locked in this battle, okay? Or you're going to just like, all right, I'm in the recursive case. I'm in the recursive case, like recurse in that direction forever until you get down to the base. And then they can all start unwinding, but you need all that memory to get up to there, okay? So that space complexity is going to be linear in the worst case. Disgusting. But really, I want you to think about it like O of h. It's going to be O of h again. The biggest height, which could have been that. Okay? Breadth first, by the way, breadth first is, it's using a queue in the worst case. Let's talk about, again, you're gonna visit all the nodes, so it's still like you're doing constant work printing each node. It's still linear time for breadth first. But for space, you have to think about like how big is this queue ever going to be? Because like you are popping stuff out of it, aren't you? So it's not going to hold all the nodes out ever, all at once. What's the worst case? How many things are going to be in the queue at once? Because like that's your bottleneck, right? You have some other pointers lying around, but like how many things are in the queue? How many pointers are sitting in my queue right now? That's going to be what gives you your space complexity. That's going to be the ultimate thing. Okay, for breadth first. So if you think about it, the worst case is when you have a complete tree, a perfect tree that looks like this, where you've pushed, like you visited this node, you pushed its children, you visited these two nodes who have then pushed their children, and for a split second then, the entire last row is sitting in your queue. Does that make a little bit of sense? Because that's what's going to happen. For a split second, like you pushed all these guys, you're still like working on this one, you visited it, it's off the stack, and then you push this one's children, and then the queue looks like this. You've pushed all the children, but you have not yet visited the children of that next level. All right? Because it's always level order, so you got to visit this one next while these guys are waiting to be visited. Yeah, and you're pushing its children at that same time, so it's going to be the last row sitting on your queue for that reason. Okay? I hope that makes a little bit of sense. And so you can imagine a giant tree that is perfect. It gets pretty large when you get you've pushed all of these the second to last nodes, and so all of their children then, you visited all of the second to last row of nodes, level of nodes, and so you pushed every single one of their children and you have not visited them yet by the time you get to this last one, right? And so you got a queue with that many nodes on it. That one, then that one, then that one. All of the last row. If it's a perfect tree, you've got all of those things. And if you think about it, what are the sizes of perfect trees? They're always powers of 2, right? Powers of 2 minus 1, so that's a size 7 tree. The next level bigger would have been a size 15 tree, right? And so how many nodes are in the last level of a tree that looks like this? More than half of them. Does that make sense? That's disgusting, but that's how that works. So that means there's about n over 2 nodes sitting in the queue in the worst case once you get to that part of that kind of tree, all right? So honestly, this would have been a better tree to go through for breadth first. But yeah, so it would be n over 2 is still, the 2 over 2 goes away. It's still linear space then. You're going to store n over 2 node pointers in that queue. Question?
Is it also 2 to the height? Or...
2 to the height? That's proportional, yeah, that's true. For this tree at least.
Oh.
Because if it was this tree, you would have popped all those guys and it would just be one node on your queue right now. So it's not true for that kind of tree, but for a complete tree that's like the number of nodes is proportional to the height, then that does happen. Yes. Yeah. Other questions? So that's some weird analyses. You'll read more about those, of course, but that's at least a good start. Are there any questions about what we talked about on this slide? It was more hand wavy, I would say, because it's harder to do like a concrete analysis of recursive stuff in a 41 class. But this is a good start. Just like, at least at a high level, you're visiting all these nodes just once. You're maybe printing them. That's linear time, for sure. Okay, regardless of how we got there. So yeah, I think that's what I wanted to say for those. Are we ready for one last recursive example that I will code up for you? Just to drive it all home. So, okay, well, let's do it. I would like to calculate the depth of a node in the tree. All right, so let's see. This is a weirder one. It's going to involve parent pointers for fun. You could make a similar algorithm that calculates the height of the tree. Think about it that way as well. But this one will be fun. I might give you the height one in a lab, actually. Let's code this one. So you're getting a node. So you're getting a node in the tree somewhere. It does not have to be the root anymore. Like you're maybe given this node. Like, I want to know the depth of the 10 node, please. This can be it's probably easier to make a while loop out of this, but it can be recursive too. Give me the depth of that 10 node. The output's going to be how high up in the tree, or how deep in the tree it was. And so essentially, you want to move parent pointers. You want to be like, all right, the depth of this node, it's that many, 1, 2. Yeah, I kind of want to get to there. And so it's going to involve the depth of its parents. You're going backwards this time, which is a good example of going the other way. So yeah, the output's going to be the depth of that node in the tree. This is at level 2, so it's 10. And so essentially, you're just going to keep visiting parent pointers recursively, because eventually, if you visit parent pointers, you'll get to the root, and the parent of the root is nothing. Okay? And so I just want to keep on going. Start at 10, go to 8, then go to 7, and then go to nothing at all. Okay? So keep on visiting the parent recursively, and once there isn't one, you're done. And this is essentially the recursive case. My depth at 10 is 1 more than the depth of my parent. Does that make sense how that's recursive? It's like, all right, hand off the problem to my parent now. I'll eventually make my way down to the base case, which is there is no parent. Just like in the other direction, you make your way down to a leaf where there is no children. So that's the recursive case. And so depth of 10 will call, all right, my answer is 1 plus the depth of 8, the 8 node itself. And it's like, all right, my answer is 1 more than the depth of 7, and that will eventually notice that, okay, yeah, the answer is 0. I'll return 0. I'm done. I'll add 1 to that. I'm done. And then, all right, the depth of 10 is like, all right, I'm 1 more than this one, so I'm 2. I'll return that. Boop, to whoever called me. So the base case is when you're at the root, you could eventually say the base case of an empty tree is -1 as well. That would also work. What's the depth of an empty tree? Negative. But you can just stop at the root. That's another example of like stopping before nullness. That's why we're doing this example. So you can just like change your base case to fit the problem at hand. So the root, let's say, if we notice we're at the root, the depth is 0. Okay, so the depth of 7 will give back 0. Depth of 8 was like 1 plus that is me, so 1. Depth of 10 was like, all right, 1 plus that is me, so 1 plus 1 is 2. Okay, does that make sense? Questions about that algorithm? Because it turns into code pretty simply. We just follow it. But that will give us a depth. It's kind of neat. So, okay. So let's say I want to call that on my 10 node. So I do have this tree. The 10 node, to get to the 10 nodes, the roots, right. Go right twice from the root. So let's get a pointer to that real quick. We'll call it 10 is roots right. There's that one. And so I want to have like a depth function. Depth of the 10 node. What's the depth of the root maybe? And then just for fun, like what's the depth of 5? That should be 1. That's roots left. Something like that. There's my depth function. And it's going to look like this, right? It's going to take a tree node, like the root of the tree you want to find the depth of, I guess. Or let's just call it n. There's a node I want to find the depth of. Give me that depth as an int. It's called depth. Cool. And so I'm in either a base case or a recursive case. The base case this time is when I'm at the root. To notice that I'm at the root, I look at parent pointers. So if n's parent is nothing, the only time that's true is when I'm at the root, right? Base case. We're at the root of the tree. Depth is 0, so I'll return 0. Otherwise, I'm in the recursive case where I do have a parent, a real parent, and so my depth is 1 plus my parent's depth. That's what I can return. Return 1 plus my parent's depth. I guess I can do this in a variable, but we could have just called it. So like, what this means is we have a parent, right? So we can recurse. We can go down, we can go up, really. Get the depth of our parent recursively, and then add 1 to it. So we'll do it this way. Depth of parent is me calling depth on n's parent. So I'm getting closer. What's getting smaller is my distance to the root. That's why the recursion works. And then our original node's depth is 1 plus that. Our original node's depth is 1 more than its parent's depth. So 1 plus that. You could have just called it right here, but we're splitting it up for fun. And so I got 2, 0, 1, which is what it should be. The depth of the 10 node is 2. The depth of the 7 node is 0. The depth of the 5 node is 1. So I was happy. Any questions about this example? Kind of neat. Let's see here. Yeah, so there's one last thing I want to do just to keep your minds in where I want it to be. After that, I need to give you a lab still, but if you will humor me for just one more instant, you do not have to write it down. Just give you a few minutes to hang out and talk to each other. A good excuse for that is this question. All right. So where we are going is I have a binary search tree, or just a tree in general, honestly. I've got a tree, and I would like to get rid of things. We've talked about insertion. I would like to remove things now. That's important. That's going to mess a lot up, depending on what I want to remove. Say I wanted to remove the 7. Now I've got 2 subtrees floating around. What do I do? That's disgusting, all right? So let's pretend this is a binary search tree. What happens? What needs to happen? How could I talk about, please? How should I delete the 6 node? Want to get rid of that one? That's kind of easy. Yeah, you kind of see that one might be easy. How would I delete the 8 node? That's harder because the 10 needs to stay, right? And then finally, how would I delete maybe the 7 node? Ooh, disgusting. So think about those things and try to come up with some algorithms just in your mind. Just like talk to each other. You don't have to write this down anywhere. Just discuss for a few minutes your algorithms to maybe deal with this stuff, because some ways are harder than others. So try to come up with an idea, and we'll talk about the real algorithms next time. I'll give you a few minutes. And then we'll talk about your lab. Remember, there's parent pointers and a bunch of night pointers to deal with. I mean, make the tree forget, while also keeping everything else that needs to be there. Right. How will you reorder things? Rearrange the tree so that it's still a BST maybe when you've chopped it. And then get rid of it. That would work. A little tricky. Couple more minutes, and then we'll wrap up. All right. Let's come back together. So this is, I hope we notice that some versions, some nodes are easier than others to get rid of, but you still have to be a little careful. So like, I would say the 6 node, right, is the easiest. I hope you agree. And the reason is because it has no children, there are many things that we don't have to consider. So that's the 0 children. There's going to be 3 cases. 0 children case. To get rid of this node, you just have to tell the 5 you don't have a right child anymore. And of course also delete it from the heap. Does that make sense? Something like that. Is that what we came up with? Yeah. That's not horrible. The 8 node is worse. It's like, all right, to get rid of that one, that has 1 child. It's like, all right, I'm getting rid of that, which means then that the 10 node must stick around. So because it only has 1 child, I'm happy because I can just be like, all right, the parent of 8, this is your new child. You can do that, can't you? Just chop that guy off. And then you have to worry about the parent pointer of 10, but that's not horrible. And then like 10 could have been a deeper tree. it's still everything's fine, right? Everybody's happy. The tree is still there, and it's all still in order at that point. It's like two arrows become one at that point. Does that make sense? That's kind of your one-child case. Is that similar to what we thought of? Try to keep it around as much as you can. The 7-note is disgusting. That's the 2 children case. And that one's going to involve some heavy lifting, because like the second you chop that off, you got 2 trees. Oh no. Who becomes the root is now the question. Where do you place things? There's going to be a very, very neat algorithm that we'll show. It's going to decide. There's a symmetric thing. You can take the next bigger, the next smaller thing. We'll get into that, but it'll be great. And yeah, that's going to be an algorithm that is worth talking about. I hope you can imagine. So yeah, that's where we're going. And did you guys have any questions about this as you were thinking about things? Or are you just excited to know the true algorithm when we get to it? All right. If we're good, that's what I want to talk about as far as trees go. We're going to have a set of slides just dedicated to binary search trees because there's more to be said. Of course, removal is going to be a big topic. And yeah, with that, that's all that I have for the day besides the new lab. So let's talk about the next lab. If we're ready, though. Are we ready for that? All right. So lab 6. This one's hash table time. Let's go look at it. 106. Cool. Here they all are. So I am going to have you make a hash table that is living here in hash. It's called a hash map. So essentially that's what we're doing. We're making a map, right? Key value pairs, just like the map type in C++. We're using a hash table to do it. So hash map is a type that's used in a lot of languages, just not C++. They call it unordered map, but other languages call them hash maps. That is fine. We will use that word. So here is what we're doing. We are going to make just exactly like the unordered map or the map of C++. Takes 2 things as templates. We're going to do the same thing. We're going to make a hash map that takes keys to values, and those are arbitrary types. Ints to strings, strings to ints, doubles to strings, strings to characters, whatever you want. Does that make sense? That should be a thing. As long as you have a hash function on this key type K, we're good. All right. So that's what a hash map holds. Okay. And we can make a hash map for any KV types as long as we have a hash function that looks like this somewhere, that takes a K, whatever the K was, to an int. So if you want to make we're going to call it capital H for hash. We're going to make it sure that if anybody wants to make a hash map on strings, we have made a function pre-made that takes strings specifically to an int, because that's what you need. That is your hash function. All right. So let's get there. So that will be your first step. So we're going to do, because this is templated, you use the header file only for this class, but you also need these concrete functions that turn ints into ints, that turn characters into ints, strings into ints, in this way with the name is capital H for hash. We need all those functions, and these could have been implemented in a .cpp file because they're concrete, they're not templated at that point, but we're just going to be lazy and put them here. All right. So you're going to make a bunch of functions that return an unsigned int, which just means it's not negative. The name of the function is going to be capital H for hash, and it's going to take a constant reference to integers, characters, strings, doubles, so that they can be the keys of our hash maps, of our hash tables. Does that make sense? Those are your hash functions. They will give you a place to insert, to remove, to do stuff like that. We're going to do open hashing. Okay. So the very first step is to make a bunch of hash functions. All right. Should work for ints, chars, strings, and doubles. And so you need at least those. The hash function has to be called capital H for hash and return unsigned int. All right. So use it, copy and paste this one, just change this type. Keep changing that type. All right. So it's very easy to turn ints into ints. I think you can imagine what you can return very quickly right now. Ints to unsigned ints. That won't be difficult. But the other ones will take some thought. Remember my idea about strings, right? You can just like turn everybody into a string, then use your string hash function. Remember how to do that? Like go through each character. You can use the character hash function that you made, multiply them, add them, do something. Make a number out of strings, out of characters, out of doubles. It's got to be an unsigned integer. Okay? So those are your hash functions. That's step one. Then you could use those as keys of your hash map type. Then you can implement hash map itself. All right? So that one's open hashing. There's only 3 things, but here's what it means to be a hash map. Let's at least show you it being used. Here's my tests files, right? So I can make hash maps from ints to doubles, from strings to ints, like all these types as keys should be possible because we made hash functions for them. You can put anything at the other end, but I'm just doing ints for simplicity's sake. So that's what they look like when you build them. And the methods we're going to have are, of course, you have a constructor that initializes the size of your hash table. And then we have insertion and search. All right. And then here is deep down what our hash table is. Our hash table is a vector. Each is going to have table size indices, a vector of that many indices of, at each index it has a list, because it's open hashing, you might have collisions, you have to put multiple things at each index, a list of key value pairs, which I am calling hash table items. All right. And because those items depend on these types, we have to put types inside of types. So I'm going to make a private type just for us called hash table item. You can just say the name and use it from your implementation's perspective, but the user doesn't get to know about this type at all because they don't need it. Only we do. It's our key value pair type of what's going inside those lists. And it's got a thing called a key and a thing called a val. And the types are as you would expect, whatever K and V were. Does that make enough sense? That's what's going on. And so that's what our table holds. You can go to an index that your hash function took you to and start going through hash table items. Right, comparing them. So yeah, that's what's going on. And then you have these 3 methods, the constructor, the insert, and the search. Search is going to give back a pointer to a value so that it can be changed. That's what you'll do. Just return a address of the thing just so that you can potentially give it back and have somebody change it. So that will be how that one works. But yeah, that's how it will be. Here is the constructor. Just like use the table size to resize your table to that size, construct it in that way, bless you. And then you've got the other 2, insertion and search. So you know what to do, right? For insertion, you have a hash function. You're guaranteed, right? The only reason you can do this is you have made sure to call the function called hash on whatever your keys type was. Call your hash function on this thing called key. You can get back an int. That will take you to a place in the table once you shrink it down using the size, using the modulus, right? All those things need to happen. So use hash to get to an index, right? Your hash function might give you back a big number. You'll have to shrink it down. And then go see if the key is already in the table. We've implemented this kind of stuff, right? So go use my example. Go use the book's example. See if the key is already there. If it is, you update it. It's not just insertion. It's an update. Otherwise, you're going to push back a brand new hash table item with that key and that value to that index that your hash table, that your hash function and shrinking down its value got you to. All right, is it all coming back to us? Does that make sense? This is a lot at once. It's templated. You're making hash functions. You're doing the whole thing from scratch. And then the search is very similar to insertion. It's just like, all right, you go find the thing. You use the hash function called with capital H. Assume you have that for your key. Because somebody's asking for the value, a pointer to the value associated with that key. So you've got the key, hash it, get to an index of your table called table, and then go through. You're going to iterate through this list, right? Iterate through that list, return back a pointer to the actual value there. So don't make a copy of that list anywhere. Go through the actual list so you can give back a pointer to the value in that particular list so that it could be changed by somebody or just looked at. All right, but you're giving back a pointer to the value associated with that key. So go into that hash table item when you find it, find that key, give back the address of that val. Does that make sense? That's what's happening. All right, there's a lot going on. So read these comments, stare at this for a while. You'll get there. And yeah, you're going to get back a pointer. And this is also us helping ourselves in case we don't find a thing. Because if search does not find something, there's an easy value to give back now because we're going to return a pointer. We can just return null. Can't we? So that's great. Just return null if you don't find the thing now. So that's beautiful. You don't have to throw an exception. Just return null, everybody will understand that meant it didn't exist. All right? So that is hashmap.h. You're implementing a templated hash table. The type is called hashmap, key value pairs, and the underlying table looks like that. It's a vector of list of key value pairs. All right? So it's open hashing. You need hash functions for your key types. You're making the hash functions. You can make more if you want, but those ones are the ones I'm testing you on. All right? So the test file has some tests already. This one's just hash map of inst to double, just making sure I can insert these things and like the things are correct and I can insert and search. That one's easy. And then the second one is very hard. It's making sure that all the hash functions are there. It's making hash tables of all the key types that I care about. Then I'm inserting more than 42 things so that there will be collisions and making sure that the search does the right thing and gives me the stuff back. All right. So that is what's happening. And I think that is what I wanted to say. Yes. Any questions about what you'll be doing? Because after you get that, it's just like, okay, now make 2 more tests, make some wild scenarios for some hash tables. Maybe you can make string to string, make a phone book example. That would be a good test to do or something. So just write 2 new tests of your own. You got the makefile to compile it all for you. And that's really it. You're going to be implementing those things in hashmap.h. Finally, you're turning in a header file, right? Again, because it's templated. And then you're adding some tests you're going to turn this file into. Okay? So it's a little involved. Definitely start early. Are there any questions about what you will be doing? All right. The syntax is going to be a little weird. You got 2 template types involved now. So you got to say that everywhere. Template class K, comma class V. 2 different types. One could have been string. The other could have been int. We don't know. The value type can be anything. But you need the hash function. You just say its name. As long as it exists for the key type, it will compile and be happy. Okay? So that, I think, is all that I can say for now, at least. We good? We ready? All right. That was enough talking for one day. So that's all that I've got for us. And the rest of the time is all yours.